Get ready to have your mind blown. We are diving into something truly out there today. NASA is launching an artificial star into space.
Oh, yeah, this is a big one.
Yes, you heard that right.
Like, seriously ambitious.
An artificial star in space. This is the Landolt mission, named after astronomer Arlo Landolt, who dedicated his career to measuring the brightness of stars.
And, you know, those measurements are like the foundation for so much of what we know.
Right. It sounds so simple.
But it really is.
It's so fundamental.
Yeah. This mission, though, is taking that precision to a whole other level. Like, imagine a ruler, but in space. Instead of inches, it's measuring the light from stars and galaxies.
Okay, so how do you build a ruler out of starlight? What does this artificial star even look like?
Well, it's a satellite about the size of a bread box.
Okay.
With 8 powerful lasers on it, positioned in what's called a geosynchronous orbit, about 22,236 miles above Earth. That means it stays over the same spot on Earth.
Oh, so
making it the perfect reference point for telescopes on the ground.
It's not like a giant glowing orb or something.
Not quite. You'd need a pretty good telescope to spot this one.
Okay.
But that's not really the point.
Right.
These lasers are incredibly precise. They're actually being calibrated by the National Institute of Standards and Technology.
Oh, wow.
The NIST folks.
The ones you like?
The gold standard for measuring things like photons.
Right.
The tiny particles that make up light.
Yeah, okay, so the lasers act as a kind of standard candle. Astronomers can compare the light from those lasers to the light from distant stars and galaxies, and that'll help them calibrate their instruments for more accurate measurement.
Exactly. It's like if you're trying to measure the length of something, you need a ruler, you know.
Right.
That you know is accurate. This artificial star provides that accuracy for measuring starlight.
Okay, that makes sense. But why is this level of accuracy so crucial? What are the big questions this mission is trying to help us answer?
Well, one of the biggest mysteries in astrophysics is the expansion of the universe. We know it's expanding, and actually it's expanding faster and faster all the time.
Right.
But the question is, what's driving that acceleration?
Dark energy. Yeah, I've heard about this, but it's always sounded kind of sci-fi to me.
Yeah.
What's the deal with dark energy?
It's definitely a mind-bending concept. Dark energy is this term for whatever is causing that accelerated expansion. We can't see it directly, but we know something's going on.
Right.
We can infer its existence from its effects on the universe.
Okay.
Some scientists believe it might be a property of space itself, a kind of energy that increases as the universe expands. But to test that theory, we need incredibly precise measurements of how fast the universe is expanding at different distances.
And that's where the Landolt mission comes in.
Exactly.
So by measuring the light from these distant stars and galaxies with this super accuracy, we can get a better grasp on the expansion of the universe and therefore get closer to understanding dark energy.
Precisely. It's like trying to understand the ocean currents.
Okay.
By studying the movement of like little buoys on the surface, those tiny movements can reveal a lot about the larger forces.
Okay, that's a great analogy. So this mission is essentially laying the groundwork for a whole new era of precision in astronomy. And that precision is key to tackling some of the most fundamental questions about the universe.
It really shows how interconnected science is. Understanding something as abstract as dark energy requires us to push the boundaries of technology, engineering, and even our understanding of light itself.
Yeah, it's amazing to think about all the different fields coming together for this mission. It's not just astronomers. You have physicists, engineers, computer scientists.
Yeah.
Even students are playing a role.
Speaking of students, this mission is a fantastic opportunity for students to get involved in this cutting-edge research. It's one thing to read about these concepts in textbooks, but another thing entirely to be a part of a team pushing the boundaries of human knowledge.
Yeah, that's such a crucial point. Imagine the inspiration that comes from being part of something like this, working alongside these experts, knowing that your contributions could lead to groundbreaking discoveries.
It's the kind of experience that can spark a lifelong passion.
Absolutely. And speaking of groundbreaking discoveries, we've touched on dark energy, but what about the other big questions in astronomy? How will this mission impact our understanding of things like the evolution of stars and the search for exoplanets?
Well, let's start with stars.
Okay.
By measuring the light from distant stars with this accuracy, we can learn about their composition, their age, and how they've changed over time.
It's almost like looking back in time, right?
Yeah.
The farther away a star is,
Yeah.
the longer it's taken for its light to reach us.
Yeah.
So we're seeing it as it was millions or even billions of years ago.
Exactly. And by studying how stars have evolved over billions of years, we can learn about the processes that govern their formation, their life cycles, and ultimately their deaths.
So it's not just about individual stars, but about understanding how stars, as like the building blocks of galaxies, contribute to the larger structure
Right.
and evolution of the universe.
Exactly. And speaking of galaxies, the Landolt mission will also have a huge impact on our understanding of these vast cosmic structures. By measuring the light from distant galaxies with high precision, we can learn about their distances, their movements, and how they've changed over billions of years.
So it's like having a more accurate map of the universe, one that allows us to trace the history of galaxies and understand how they've clustered together over time.
Yes, and it's not just about mapping the universe as it is now. By looking at distant galaxies, we're essentially looking back in time.
Right.
Which allows us to study how galaxies formed and evolved in the early universe.
This is incredible. It's like we're piecing together a giant cosmic jigsaw puzzle, and the Landolt mission is providing some crucial missing pieces.
And who knows what amazing picture will emerge once we have all the pieces in place.
That's what makes this mission so exciting. It's not just about the answers we'll find. It's about the new questions that will arise as we push the boundaries of our knowledge.
And speaking of pushing boundaries, let's shift our focus to one of the most captivating areas of modern astronomy, the search for exoplanets, planets orbiting other stars. How will the Landolt mission help us in this quest?
I'm all ears. Tell me how we go from measuring starlight to finding planets light years away.
Well, one of the main methods for finding exoplanets is to look for tiny dips in the light of a star as a planet passes in front of it.
Okay.
Imagine a moth flying in front of a streetlight. You'll see a slight decrease in the light as the moth blocks a small portion of the light source.
Okay, got it.
So astronomers are looking for those tiny dips in starlight as evidence that a planet is orbiting the star.
Okay, so they're looking for those tiny dips in starlight as evidence that a planet's orbiting the star.
Exactly. But here's the thing. The more precisely we can measure the light from a star, the smaller the dips we can detect. And therefore, the smaller the planets we can find.
So the Landolt mission, with its super accurate measurements of starlight, could help us discover a whole new population of exoplanets.
Yeah.
Including those that might be Earth-sized or even smaller.
That's the hope. And not only that, but by analyzing the light that passes through an exoplanet's atmosphere, we can learn about its composition and potentially even detect signs of life.
Whoa, hold on. Are we talking about potentially finding evidence of life on other planets? That's next-level stuff? How exactly does that work?
Well, when light passes through an atmosphere, certain wavelengths are absorbed by the gases present. By carefully analyzing the light that reaches us from an exoplanet, we can identify the chemical fingerprints of gases like oxygen, methane, water vapor.
Oh, wow.
Which could be indicators of life as we know it.
So the Landolt mission, by providing these incredibly precise measurements of starlight, could be a key to unlocking the secrets of exoplanet atmospheres and potentially even answering the age-old question, are we alone in the universe?
It's definitely a possibility, and that's what makes this mission so thrilling. It has the potential to not only expand our understanding of the universe, but to fundamentally change our perspective on our place within it.
This is truly mind-blowing. We've covered dark energy, stellar evolution, exoplanets.
That's a lot.
It all comes back to this artificial star shining its light from space and illuminating the mysteries of the cosmos. It's almost too much to process.
It is a lot to take in, but that's the beauty of science. It's a never-ending journey of discovery, constantly challenging our assumptions and pushing us to explore new frontiers.
And with the Landolt mission, we're embarking on one of the most ambitious and potentially transformative journeys in the history of astronomy.
Before we get too far ahead of ourselves, I think it's important to remember that this mission is still a few years away. The launch is scheduled for 2029.
Okay, so we have some time to wait, but the anticipation is definitely building. What can our listeners do in the meantime to learn more about this mission and the science behind it?
We'll be sure to include some links in the show notes where you can delve deeper into the topics we've discussed today. You'll find resources on dark energy, stellar evolution, exoplanet research, and of course, the Landolt mission itself.
That's great. So if you're as fascinated by this artificial star as we are, be sure to check out those links. But before we move on to the next part of our deep dive, I want to leave you with a thought-provoking question to ponder.
Okay, I'm listening.
Imagine the discoveries that await once we have this level of precision in our astronomical measurements. What mysteries of the universe might we be able to solve? What new questions will we be asking? And how might those discoveries change our understanding of ourselves and our place in the cosmos?
Those are fantastic questions, and the possibilities are truly endless. Perhaps we'll finally crack the code of dark energy, or maybe we'll discover evidence of life on other planets, or maybe we'll uncover something completely unexpected, something that revolutionizes our understanding of the universe as we know it.
That's the beauty of science, isn't it? It's full of surprises. And the Landolt mission is poised to unlock a whole new realm of cosmic wonders. Stay tuned for part 2 of our deep dive, where we'll delve deeper into the technology behind this incredible mission and explore the potential impact it could have on our world.
Sounds good. It's amazing when you think about the technology that makes a mission like this even possible.
I know, right? We're building this little instrument that has to work perfectly in space.
Yeah, and withstand temperature extremes and radiation, and all while staying in a stable orbit and making sure those lasers are pointing with pinpoint accuracy.
And where is all of this happening?
Mission control for the Landolt mission will be at George Mason University, right here in Virginia. But the satellite itself is being built in partnership with NIST.
Okay, so NIST, the National Institute of Standards and Technology.
Right.
What role are they playing in all this?
They're the precision experts. Like, they're making sure those lasers are calibrated perfectly.
So how do they do that?
It's a really complex process. They have to account for everything you know, from the materials used to build the lasers to how they're powered in space, to make sure the light emitted is super consistent and accurate.
So is that like a bunch of scientists huddled around a workbench calibrating each laser?
You're not far off. Think clean rooms, specialized equipment, and a lot of precision. It's not just about the lasers, though.
Right.
They also have to develop the systems to control those lasers.
Oh, right, to make sure they're pointing the right way.
Right, and account for any disruptions.
Disruptions. What kind of things could mess with the measurements?
Space debris.
Oh, yeah.
Even tiny particles traveling at high speeds could damage the satellite or, interfere with the lasers. Then you have the Earth's atmosphere, which can distort light.
Right. So how do they deal with all of that? It seems like a constant battle.
It is. The mission scientists and engineers are coming up with algorithms and models to compensate for these potential issues. They're also designing the satellite to be as tough as possible.
So like backup systems.
Right, with redundancy built in.
It sounds like they're really going all out.
Absolutely. And it's not just about the technical challenges. There's also the data, like a massive amount of data this mission will generate.
Yeah. How do you even handle all that information?
It's going to require powerful computers, sophisticated algorithms, and a lot of brain power. Fortunately, there's a whole field of astronomy dedicated to analyzing large astronomical data sets.
So it's like a village.
Yes. Very much so.
To make all this happen.
Right. From building the satellite and calibrating the lasers to actually making sense of the data.
Right. And we talked about students getting involved earlier.
Yes.
What kind of opportunities does this mission present for students?
The Landolt mission gives them a chance to get hands-on experience with all kinds of things. From designing components of the satellite to developing data analysis tools to conducting their own research using the data.
Wow. So it's not just textbook stuff.
No, it's real-world experience.
Yeah, that's fantastic. So the Landolt mission is not just about the universe, but about cultivating future scientists and engineers.
It's about inspiring that passion for discovery.
I like that. Okay, so we've talked about the data, the students, but let's get back to the science. We talked about dark energy, stellar evolution, exoplanets earlier. I'd love to dig a little deeper. Let's start with dark energy. What are we hoping to learn about dark energy specifically?
One of the big questions is whether dark energy is constant. Or if it changes over time.
And that's important because
if dark energy changes, it could mean big things for how we understand the universe's evolution. And its fate. The Landolt mission is going to help by giving us super precise measurements of the expansion rate of the universe at different points in its history.
So how do those measurements tell us if dark energy is constant or changing?
If dark energy is constant, the expansion should change in a predictable way. But if dark energy is changing, those predictions won't match what we see. So we can compare the measurements with the models to gain insights into the nature of dark energy.
It's like we're using the light from these stars and galaxies as a cosmic clock. To track the expansion of the universe.
Exactly.
So dark energy is one piece of the puzzle.
Right.
What about stellar evolution? What are we trying to figure out there?
Well, one of the things we still don't fully understand is how stars form.
It seems so basic, though.
It does, but the details of how gas and dust clouds collapse and ignite into stars are still pretty mysterious.
How will the Landolt mission help with that?
We can use the light from distant stars to figure out their ages, their masses, and what they're made of.
Okay.
And this will help us trace their evolution.
Okay, so it's like a cosmic family tree.
Yes.
Tracing their lineage back to the early universe.
Precisely. And by learning how stars formed in those early times, we can better understand how galaxies formed.
Right, which ultimately leads to understanding how the universe as we know it came to be.
Right.
Incredible. We've talked about the big questions.
Mm.
But what about the practical stuff? Could there be benefits from this mission for us here on Earth?
That's a great point. While the main focus is scientific discovery, space exploration often leads to unexpected practical applications.
Like what? Give me an example.
Well, GPS, for example. It relies on satellites that were originally developed for science in the military.
Right.
But now we use GPS for everything.
Yeah, it's a good one. So what about the Landolt mission? Any potential earthly benefits on the horizon?
Hard to say for sure.
Okay.
But the precise starlight measurements could lead to improvements in things like telecommunications
Okay.
or optical communications,
Mm-hmm.
even laser technology. And the tech developed for the satellite could be used in other areas like remote sensing.
So while we're looking out to the stars, we might also find solutions to problems here on Earth.
Exactly. Science isn't just about distant galaxies.
Right.
It's about understanding the world and finding solutions.
That's a great way to put it.
Mm-hmm.
So as we wait for launch in 2029,
Yes.
we can be excited about both the big discoveries
Yes.
and the potential benefits for everyone.
Absolutely. And as we continue on this deep dive,
Okay.
let's remember, this is just the start of an amazing journey.
Okay.
Stay tuned for part 3, where we'll look at the long-term implications of the Landolt mission and the future of astronomy.
Sounds good. So we've talked about lasers and dark energy and exoplanets.
It's a lot.
But what about the big picture? What's a lasting impact of this mission?
Yeah, it's really interesting to think about. The Landolt mission isn't just one experiment.
Right.
It's a foundation for so many future discoveries.
So it's not just about answering today's questions, but about giving future scientists the tools to ask even bigger questions.
Exactly, like building a new observatory.
Okay.
You're not just looking at what's visible right now.
Right.
You're setting the stage for countless observations and discoveries down the road.
And with Landolt, we're building that observatory in space.
Yes, a virtual observatory providing data for decades to come.
And that data is going to impact so many areas of science.
Oh, absolutely. The precise measurements of starlight, it's not just dark energy, stellar evolution exoplanets.
What else?
It could lead to breakthroughs in cosmology, astrophysics, even fundamental physics.
Wow, so it's like a ripple effect.
Yes, exactly.
Spreading out across the scientific landscape.
Yeah.
So what specifically beyond what we've already talked about might be impacted by this?
Well, cosmology, for one, that's the study of the universe as a whole.
Right.
The precise measurements of the expansion rate will really refine our understanding of the Big Bang and the early universe.
So we're learning about the fundamental forces that govern the universe.
Exactly. And then there's astrophysics, which studies the physical properties of stars and galaxies and everything.
Right.
The Landolt mission is like giving astrophysicists a new set of eyes.
A way to see the universe in more detail.
Yes, exactly. And let's not forget fundamental physics, the study of the basic building blocks of matter.
Mm-hmm.
Those precise measurements could even help us test Einstein's theory of general relativity.
Wow, so a mission about stars could impact our understanding of the most basic laws of nature.
It really shows how interconnected science is. Discoveries in one field can have huge implications for others.
And it highlights why it's so important to invest in this kind of research.
Absolutely, even if we don't know the practical applications right away.
You never know what doors it might open.
Right, exactly. And speaking of unexpected benefits, what about the impact on society as a whole? Not just the practical applications, but the cultural implications, too.
Okay, I'm curious. What kind of cultural impact?
Well, for one, it could inspire a whole new generation of scientists and engineers.
I could see that.
The ambition, the ingenuity pushing the boundaries.
It's exciting.
It's a message to the world that anything is possible.
Mm-hmm.
And it's not just about the next generation of scientists.
Right.
It's about igniting a sense of wonder in everyone.
Oh, I love that.
Those images and discoveries will captivate people.
It really will.
And remind us of our place in the universe.
Yeah, it's that feeling of being part of something much bigger than ourselves.
Yes, exactly. It can be humbling and empowering at the same time.
So it's not just science. It's about broadening our horizons challenging our thinking and inspiring us to dream big.
Well said. As we wrap up this deep dive, I want to leave our listeners with one final thought.
Okay.
The Landolt mission is really a testament to human curiosity, to our ingenuity, and our ability to work together.
To achieve amazing things.
Yes, and as we look ahead, let's hold on to that spirit of exploration and discovery.
Right.
The journey is just as important as the destination.
And who knows what we'll find out there.
The universe is full of mysteries.
So many.
And this is just one step in our quest to solve them.
Well, this has been an incredible journey. Thanks for taking us on this deep dive into the Landolt mission and the future of astronomy.
My pleasure. It's been fun.
To our listeners, keep looking up, keep asking questions, and never stop exploring.
Couldn't have said it better myself.